Hello students, in this video we're going to be talking about asymptotes. There will be many problems on your homework 10 that ask you about the asymptotes of a function. So the basic definition of an asymptote, this isn't the formalized math definition, it's just kind of a common understanding, but asymptotes are dotted lines that your function will get arbitrarily close to, infinitely close to, but will never cross. And asymptotes can be vertical, horizontal, or oblique. Oblique just means diagonal. So let me just show you a picture of what an asymptote looks like. If we have this function, the blue line here, it's going to go forever in these two directions. As these two directions continue on and on and on, it's going to get closer and closer and closer to this red dotted line. But it'll never, ever, ever actually touch it. It'll just keep getting closer and closer forever until you would need a microscope to see the difference. That's an asymptote, that red line. So notice that this function actually has two different asymptotes. It has a horizontal asymptote that our line will get closer to this way and off to the left, and it has a vertical asymptote, a straight up and down asymptote that our function will get closer to on both the top and the bottom as we go out further and further toward infinity. So that's just kind of a conceptual understanding of what asymptotes are. Notice that they're lines. Asymptotes will always be lines. We can describe horizontal lines as y equals some number. We can describe vertical lines as x equals some number. And we can describe diagonal lines or oblique lines as y equals mx plus b. Linear equations, slope, y-intercept. So the three types of asymptotes that you need will always be in the form of y equals blank or x equals blank, where that blank could be a number or it could actually be like a diagonal linear equation. Whoops. So let's look at question 9 together. This is a conceptual question. They give you a graph of f of x, and they want us to estimate what the x and y intercepts are. So first we're just going to find those. I see a y-intercept here, and I see an x-intercept here. Now, we'll never have any other x-intercepts because as this line goes further this way, it's kind of going down. And this line, this part of our function, will never cross the x-axis because it can't get above this asymptote, right? So we've already identified our only x-intercept. And for the same reason, we'll only have that one y-intercept. Also because this is a function and you can't have 2 points on the y-axis. So to estimate within 5 units what our intercepts are is going to be pretty easy because they fall on intersections. Our x-intercept is at 2, 0, and our y-intercept is at 0, 3. Now they're asking us to estimate what our vertical asymptote is. We're looking at this red vertical line. That is the line x equals -2. So we're going for our x value there. And our horizontal asymptote is this horizontal line that's at the value y equals -3. So we'll just put in -3 right here. They're also asking us for the domain of f of x. Now, the domain is the set of all x values that we can put into our function. And domain and asymptotes actually go hand in hand. So if I'm looking at my blue function, all of these x values going down to infinity will be included in my function. All of these x values are included all the way up to this part. This vertical asymptote, remember an asymptote is a line that your function will not cross. The vertical asymptote here is not going to have any x values represented on it for our function. So actually, this is not included in our domain. But all of the points to the right of it are, because our function starts back up immediately on the other side of this line, or at least infinitely close to it, and continues forever. So our domain is going to be all real numbers except for the place where we had that vertical asymptote, which was -2. There was another question on the common homework that was very similar conceptually to that one, so we're just going to do this one too just for some extra practice. They're asking us again to find our x and y intercepts. So I see a y-intercept here and an x-intercept here. That will give us, let's see, 4, 0 for our x and negative, or 0, -4 for our y. Our vertical asymptote is this line here. I know earlier I described it as a dotted line. It looks like they're using a solid line, but same concept. Our vertical asymptote is this vertical line that passes through x equals -2. And our horizontal asymptote is this horizontal line that passes through the point y equals 2. And they want to know the domain. Again, the domain is going to be closely tied to your asymptotes. Look at this vertical asymptote that goes through x's -2. This whole vertical line is a place where we will never have any values of our function represented because our function can't cross this line. So we will never have -2 as a value in our domain. Let's move on to a more algebraic representation of asymptotes. There are a lot of notes on your screen, so you might want to pause your video and write these down, or pull out your cell phone, snap a picture of this so that you have a copy of all of these notes. If we want to find asymptotes algebraically, meaning we don't have a graph, we don't have a picture, we're actually just given the function formula itself and we need to find asymptotes, there are 3 different types of asymptotes you have to look for. Vertical asymptotes, the ones that go up and down, horizontal asymptotes, the ones that go left, right, and oblique asymptotes, the ones that go diagonal. So we haven't seen an example of a diagonal or oblique asymptote yet. If I have a function, let's say it looks something like this, and like this. This would be a function that has a vertical asymptote here and an oblique asymptote that goes diagonal. So it's not horizontal, it's not straight left, right, it's kind of diagonal. So now we're going to talk about how to find these different types of asymptotes. To find our 3 different types of asymptotes, there are 3 very different methods we need to use. Vertical asymptotes come from places where the denominator of our function equals 0. Notice that this concept is closely tied with domain. The domain of a function, when we want to find values that are not included in our domain, we set the denominator of our function equal to 0, and that gives you x values that your function can never be equal to because it would make your function undefined. So vertical asymptotes, closely tied with domain. To find horizontal asymptotes, we're going to do something entirely new. You may have never seen this before, so let me break this down. We're going to compare the degree of the numerator with the degree of the denominator. Remember that degree is the biggest exponent. So let me just write, I'm going to write 3 examples over to the side of the screen. So in example 1, let's say we have x to the 4th minus 3x squared plus 1 over 5x minus 3, something like that. In example 2, I'm just going to write 4x to the 9th minus 6x plus 17 over 8x to the 20th minus 2. And for example 3, we'll do 6x cubed plus 4x squared minus x minus 1 all over, let's do negative 5x cubed plus 3x. Okay, good enough. That took me a while to write those examples down, but I wanted to demonstrate 3 very different cases here. If we're looking for horizontal asymptotes, first you have to identify the biggest degree on top and the biggest degree on bottom. So in each of these three examples, we would just need to find our biggest degree. So this biggest degree would be 4, and then on the bottom, the biggest degree is 1. Sometimes you actually have to write in an exponent if there isn't one there. In example 2, our biggest degree on top is 9, our biggest degree on bottom is 20. And in example 3, our biggest degree on the top is 3, and our biggest degree on the bottom is 3. So now that we've kind of identified what the degrees are, let's talk about how we compare them. If the numerator degree is bigger than the denominator degree, so top is bigger than bottom, there is no horizontal asymptote. So that's our first example here. Our top degree is 4, our bottom degree is 1. If the top is bigger, there is no horizontal asymptote. However, if the numerator degree is smaller than the denominator degree, then we do have a horizontal asymptote at y equals 0. So in example 2, our top degree is 9, our bottom degree is 20. If the bottom degree is bigger, it's bigger on the bottom than it is on the top, then we do have a horizontal asymptote at y equals 0. It's always 0 in this case, always 0 if the bottom is bigger. Finally, we have the case where our numerator, our numerator degree equals the denominator degree. If they're the same, such as here in example 3, then we have a horizontal asymptote at the top leading coefficient divided by the bottom leading coefficient. And that's easier than it sounds. It's 6 over negative 5. 6 over negative 5, just the leading coefficients, or negative 6/5. And sometimes in an example like example 3, you'll end up with something that simplifies. Like if you had, let's say 8x to the 9th plus 2 over 4x to the 9th minus x cubed. Our biggest exponent on top matches our biggest exponent on the bottom, so our answer would be, we'd have an asymptote at y equals 8 over 4, which is, y equals 2. So you can simplify these, of course. And I wrote this one wrong. It's an asymptote at y equals 6 over negative 5. Excuse me. So we've talked about vertical, we've talked about horizontal, now let's talk about oblique. Believe it or not, oblique is the tough one. It's even tougher than horizontal. Oblique asymptotes exist if the numerator's degree is 1 bigger than the denominator's degree. So we did example 1. Example 1's numerator degree is bigger, but it's not bigger by 1. So we've got a 4 and a 1. If we had a 4 and a 3, then we'd be in business. But it's a 4 and a 1, so this example would have no oblique asymptote. In fact, all of these examples, 1, 2, and 3, none of them have oblique asymptotes because the top exponent is not 1 bigger than the bottom exponent. So let me write an example here where we would have an oblique asymptote. Let's say 7x squared plus 2x minus 1 divided by x plus 3. This would have an oblique asymptote. Now be careful, it doesn't have a horizontal asymptote because the numerator is bigger than the denominator, so there's no horizontal asymptote. There is an oblique asymptote because 2 is 1 degree bigger than 1. So yes, we have an oblique asymptote. How do we figure out what it is? To find it, you must complete polynomial long division, or we can do synthetic division. That's a shortcut. Ignore the remainder if there is one. So we're going to display examples like this just as we go through problems in this video. I won't complete this problem right here, but we'll see examples here in a minute. I also want to remind you just about finding x and y intercepts. Some of these questions are going to ask us to find those. To find x-intercepts, you set y equal to 0, solve for x. To find y-intercepts, you set x equal to 0, solve for y. All right, so our first question here that we're going to do all the way through says to consider this rational function. find the vertical asymptotes, horizontal, and oblique asymptotes. Then we also need to find domain, x-intercept, y-intercept. So let's start with the easy stuff. Let's do domain and the intercepts first. So, let's just do the intercepts first. If we want to find the x-intercept of our function, we let y equal 0 and we solve for x. So we would get 0 equals 3x minus 3 over 3x squared plus 11x plus 6. Now I'm going to multiply both sides by 3x squared plus 11x plus 6. And on the left, we'll still have 0. But on the right, this cancels with this, and we end up with 3x minus 3. And now it's very easy to solve for x. We get x is equal to positive 1. So our x-intercept is at x equals 1. Where does that go? 1 comma 0. Now to find our y-intercepts, our y-intercept is where we set x equal to 0 and solve for y. So here we would let y equal 3 times 0 minus 3 over 3 times 0 squared plus 11 times 0 plus 6. So that's going to give us y equals negative 3 over 6, which is negative 1/2. And we'll put that right here. Okay, we will talk about domain in a minute. Let's move on to vertical asymptotes, horizontal asymptotes, and oblique asymptotes. So we'll start with vertical. Vertical is the easiest one. So for vertical asymptotes, we have to set the denominator equal to 0. So that'll be 3x squared plus 11x plus 6 equals 0. Solve for x. So we can solve this, since this is a quadratic equation, we can solve it any number of ways. We can factor, we can use the quadratic formula, or we can complete the square. I want to see if this factors. Usually if it factors, that's the easiest way to do it. So we'll do 3x, x, 3, 2, plus, yeah, this factors into 3x plus 2 and x plus 3. Now we can take each factor, set them equal to 0. 3x plus 2 equals 0, x plus 3 equals 0. We end up with x equals negative 2/3 and x equals negative 3. We found 2 vertical asymptotes. And in fact, they gave us 2 blanks to fill in. So they ask us to put it from smallest to largest. So we're going to do our smaller one first, which is negative 3. And then our next one is negative 2/3. The reason I wanted to hold off on domain is because vertical asymptotes and domain go hand in hand. So when you find your vertical asymptotes, you can usually just go up and fill in domain very easily. Remember, we got the vertical asymptotes by setting the denominator equal to 0. And wherever the denominator equals 0, that's undefined, or that's a place that can't be in your domain. So we can just take these values, negative 3 and negative 2/3, and plug them in right here for that answer as well. Okay, the next question. Find any horizontal asymptotes. That's where we compare degree from the top and bottom. So we have 3x minus 3 over 3x squared plus 11x plus 6. Our top degree is 1, and our bottom degree is 2. The rule is, if the bottom degree is bigger, you have a horizontal asymptote at y equals 0. It's always 0. So we do have a horizontal asymptote at y equals 0. Here's the thing. You can only have one of these. You cannot have both a diagonal asymptote and a horizontal asymptote. So in a problem like this, if you find a horizontal asymptote, you don't have to look for an oblique asymptote. You can stop here. So we're done. Now, the last part of the question asks us to choose a graph that best represents the function, and we're going to use our answers from previous parts of this problem to do that. So our function has an x-intercept at +1, so that would be here. This function's looking okay. This function's looking okay. This function, I can't really tell, but that could go through 1. So they all check out for this piece of information. Now let's look for our y-intercept, should be at -1/2. So this one looks good. This one looks good. This one, however, does not. So C is out because it doesn't have the y-intercept. Now let's look for vertical asymptotes. We need a vertical asymptote at -3 and -2/3. This one does have a vertical asymptote at -3, but B does not have a vertical asymptote at -3, so we can cross that one off too, and we're down to just A. All right. Now let's move on to another very similar example. We have a rational function. We want to find the domain, the vertical asymptote, horizontal or oblique asymptotes, and intercepts. So I'm just going to jump in. I think that you guys can do these intercepts on your own. That's a pretty simple type of problem to do, so I'm going to skip that in the video, and I'm just going to look at asymptotes. So we'll start with vertical. Vertical is the easy one. We set the denominator equal to 0. So that'll be x - 1 = 0. Solve that for x, and you get a vertical asymptote at x = 1. Vertical asymptote at x = 1. That also answers our domain question, because our domain cannot include the number 1 because that would make our denominator undefined. Okay, next question. Horizontal asymptote. So we start with our function, -3x - 4 over x - 1, and we compare the degree of the top with the degree of the bottom. It's 1 over 1. So what we do is we take the coefficient in front of that leading term, which on the bottom here, since there's nothing written, we would imagine this was a 1x. We will have a horizontal asymptote at y equals -3 over 1. Remember, if our degree of the top matches the degree of the bottom, then we just use the coefficients. So -3 over 1, that simplifies to -3. So we have a horizontal asymptote at y equals -3. And since we have a horizontal asymptote, we don't even have to look for an oblique asymptote. So find your intercepts, pick the right graph based on the information you have, and then you're smooth sailing. Our next problem, again, is very similar. They ask for the same type of information. So let's start by trying to find our asymptotes. To check for vertical, we let the denominator equal 0. So that's going to be 12x squared minus 14x minus 10. And we solve for x. So we could factor, we could use the quadratic formula, or we could complete the square. I'm going to try to factor. So I'm going to take a 2 out. And then I'm going to factor what's in the parentheses. Sometimes these don't factor, but I'm hoping this one will. We're definitely going to need a 5 and a 1. How about 2x, 3x minus 10 plus 3? That works. So we factored this. Now we can set each of our factors equal to 0. 2x plus 1 equals 0. 3x minus 5 equals 0, and solve for x. So we get -1/2 and positive 5/3. These are our two vertical asymptotes. So we plug those in as our answer. They want us to write them from small to big, so we're going to put the -1/2 first and the positive 5/3 second. These two pieces of information also answer the question about domain. Since these are places where our denominator equals 0, our domain cannot include these two values, so we can put them right here as well. Now let's deal with horizontal asymptotes. To do horizontal, we have to compare our top exponent and our bottom exponent. So we have x minus 3 over 12x squared minus 14x minus 10. Our top exponent, our biggest one, is 1, and bottom is 2. So we will have a y-intercept at y equals 0. If your bottom exponent is bigger, or your bottom degree is bigger, you have a horizontal asymptote at 0. And since we have a horizontal asymptote, we don't even have to look for oblique. So you're probably getting kind of tired of this. We haven't even seen an oblique asymptote yet, so welcome to question 19. Hint, hint. In this equation, we've got an x squared over an x. Actually, let's do vertical asymptotes first. For vertical, we set the denominator equal to 0. So that'll be x minus 3 equals 0, giving us an asymptote at x equals 3. So our vertical asymptote here would also answer a question about domain, but we don't have a question about domain in this problem. Well, that's convenient. Let's do horizontal. We have x squared minus x minus 9 over x minus 3. Our top exponent is bigger than our bottom exponent. So that means there is no horizontal asymptote. So now we have to move on to oblique. For oblique, we're still comparing the degree on top to the degree on bottom. If the degree on top is 1 higher than the degree on bottom, then we have to check for, then we will have an oblique asymptote, and we have to do a calculation to find it. Here's how you do that. You actually have to do the division problem. X squared minus x minus 9 divided by x minus 3, you have to actually divide. So you have two choices. You can use polynomial long division, or you can use synthetic division. And just because this is the first problem, I'm going to do it both ways. I won't do this on the next example, but I just want to remind you what polynomial long division looks like and what synthetic division looks like. So for polynomial long division, we'll put our divisor on the outside of a bracket and our divisee on the inside of the bracket. So x squared minus x minus 9 divided by x minus 3. Now we have to figure out, what do we multiply by x to turn it into an x squared? What do you multiply by x to turn it into x squared? The answer is just x. Now we take that x and we multiply it by the divisor, x minus 3, and that result goes on our next line. So that would be x squared minus 3x. But since we're subtracting this line, you have to switch both signs. And on the next line, we will combine all like terms. So our x squared, negative x squared, those combine, but that gives us 0. Our negative x and positive 3x combine and give us 2x. And then our negative 9 does not have anything to combine with, so we just rewrite it. Next step, we ask, what do I multiply by x to get 2x? What do I multiply by x to turn it into a 2x? And that would just be positive 2. So now we take that positive 2 and we multiply it by our divisor, x minus 3, and that result goes on our next line, 2x minus 6. But since we're subtracting, we have to switch this sign and switch this sign. So on our next line, we combine all of our like terms. The 2x and the negative 2x combine and cancel. The negative 9 and the positive 6 combine to give us a negative 3. Negative 3 is a remainder. X cannot go into negative 3, so we are done now. We end up with x plus 2, remainder, negative 3. Here's the thing. When you are trying to find an oblique asymptote, you have to divide. After you're done dividing, you can completely ignore your remainder. Whatever you ended up with, except for the remainder, just ignore that, is the equation of the line that is your oblique asymptote. So our oblique asymptote is y equals x plus 2. Now this is a line, right? This is the line 1x plus 2, so it has a slope of 1 and it has a y-intercept of 2. We could draw it on the graph. So y-intercept of 2 would be right here, a slope of 1 would be like this, so our oblique asymptote would go just like that across our graph. So this is a line that our function would not cross. Now as soon as I say this is a line that our function would not cross, we're going to encounter a question that talks about whether our function crosses the oblique asymptote. So we'll get to that in a second. I'm going to kind of talk out of both sides of my mouth here for a second. So our answer was y equals x plus 2. I'm not going to find the x and y intercepts. I think that's something that you guys can handle on your own. But I do want to talk about the next question. Does the function r of x cross the horizontal or the oblique asymptote? So in this case, we're talking about an oblique asymptote. Does our function cross the oblique asymptote? Well, if they would cross each other, so I'm just going to draw two kind of random things. So let's say this is our function and this is our asymptote. If these two things cross each other, there would be a point of intersection. A point of intersection is a place where two things are equal to each other. So basically the whole, the process is, if they cross, then there will be a place where they are equal. So what we have to do is, if we want to know if r of x crosses our oblique asymptote, we set r of x equal to the oblique asymptote, and we see if we get an answer. So r of x is x squared minus x minus 9, and our oblique asymptote is x plus 2. Let's see if this makes sense. So, oh, I didn't write the whole thing. R of x is actually over x minus 3. There we go. So all we do is we try to manipulate this and solve for x. So since I have a rational expression on the left-hand side, I want to get rid of that denominator. So I'm going to multiply both sides of my equation by x minus 3. On the left, they cancel. So I end up with x squared minus x minus 9 equals x squared minus x minus 6. Now, remember we have to keep our equation balanced. I'm going to subtract x squared from both sides. And then I'm also going to subtract x from, or add x to both sides, excuse me. And that's going to leave me with negative 9 equals negative 6. Well, in math, that's called a contradiction. Negative 9 does not equal negative 6. So I ended up with something that was not true, that was a contradiction. So my answer here is a big, clear no. They do not cross each other. Now, it is technically possible for a function to cross its oblique asymptote, and let me explain why. So let's say we have two different sides of our function. Let's say the left-hand side of our function kind of goes like this. So this side has an oblique asymptote. And this line represents the oblique asymptote, the dotted line. But then the other half of our function could go something like this, where it has its own oblique asymptote maybe going through. So things like this could potentially, theoretically happen in a function. It would be a really weird function. It might have to be a piecewise function. But technically you could have a situation where one part of your function passes through the oblique asymptote from another part of your function. The problem is, even though this oblique asymptote really only applies to our function piece on the left, since oblique asymptotes are lines, this asymptote is also going to go forever in the right-handed direction too. So that's where you get that kind of strange occurrence. So you're going to have to grit your teeth and fight your way through an example if they ask you whether it crosses. You actually do need to calculate that out to see. It's not just as simple as saying, no, it'll never cross. Sometimes it does cross. My eraser's not working. Give me a second here. Okay, so I promised you a few minutes ago that I was going to do this using synthetic division too, so I just want to show you that really quickly before we move on to the next problem. We do not have to do long division. There is another way. You can rewrite your problem using a synthetic division bracket. So you take this negative 3, turn it into a positive 3, draw your bracket upside down and leave some extra space, And then we fill in the coefficients. So this coefficient would be 1, -1, and -9. So we'd put 1, -1, and -9 in our first row. Then we're going to do a little addition game where we add the 1 with the number below it, but there's nothing there, so we'll write a 1 here. Then we multiply our divisor, which is 3. We multiply 3 times the 1 we just wrote at the bottom, and that'll give us 3 right here. Now we take the -1 plus the 3, and that'll give us +2. Then we multiply 3 times 2, and that goes here. Now we add -9 plus 6, that'll give us -3, and we're done. Now you have to read this from right to left. The first number on the right is your remainder, so that's remainder -3. Then immediately to the left of that is our last term of our polynomial, so it would be a constant. And then you kind of count up in degree from there as you move to the left. So constant term, x squared term, x cubed term, x to the 4th term, etc. But since we only have 2, we can kind of stop here. I don't know, my pen is freaking out, guys. I don't know what's going on here. So we end up with 1x plus 2, or just x plus 2. So of course, same answer, much less work. It might feel a little bit like magic how synthetic division works, but if you understand the process, you can get to the same answer in a very short period of time. Question 5. In question 5, we're answering very similar questions. We want to take this rational function and find our asymptotes. So we're going to start with vertical asymptotes. We set the denominator equal to 0, and we solve for x, which just requires dividing both sides by 2. So we get the vertical asymptote at x equals 0. Now we're going to check for horizontal asymptotes. In this type of asymptote, we are comparing our top degree to our bottom degree. So let me get this rewritten here. Our degree on top is 2, and our degree on the bottom is 1. If the top is bigger, there is no horizontal asymptote. So that means we need to move on to oblique. For oblique asymptotes, we'll only have one of these if the top degree is 1 bigger than the bottom degree. And that is the case in this example. We have a 2 and a 1. So we will have an oblique asymptote. How do we find it? We use long division. I do want to point out something here that's really important. All of that synthetic division stuff that we've been talking about doesn't work when you just have a 2x, right? So in our last example, we had an x minus 3. Well, it's the minus 3, it's the minus 3 that we change and then write here. So it's the term, the constant term after the x. Well, this, first of all, isn't just an x, it's a 2x, which is also a big deal. But it doesn't have a plus or minus a constant. So synthetic division, that little shortcut, won't work on this problem. So you still need to know how to long divide. So inside our bracket, we've got -x squared plus x plus 2. And this is a bit of a complicated long division problem, so bear with me. The first question we ask is, what do we multiply by 2x in order to get -x squared? So you have to think about this one. What would we multiply by 2x to turn it into a -x squared? Well, it's going to have to be a negative number. We're going to have negative something. And then to turn a 2 into a 1, we have to multiply by 1/2. And then to turn an x into an x squared, we have to multiply by x. So we will be multiplying by -1/2 x. And then we multiply that times our divisor. We write the result on our next line. So our next line will be -1x squared. Since we are subtracting, we have to change our sign. That becomes a plus. And on our next line, we combine all like terms, which is just the negative x squared and positive x squared. So our positive x and our positive 2 just carry down. For our next step, we ask the same question. What do I multiply by 2x in order to get x? What would I have to multiply by 2x in order to get x? And similarly, we're going to have to multiply by a positive 1/2, because to turn a 2 into a 1, you have to multiply it by 1/2. So then we take this positive 1/2 and we multiply it by our divisor, which is 2x. And the result gets written on the next line, which would be x and only x. But we're subtracting, so we have to put a minus sign here. And we combine like terms. Here's our next line. We ended up with a remainder of 2, but remember, when we're looking for oblique asymptotes, we can ignore the remainder. So our answer is just this part here. So we end up with the oblique asymptote y equals negative 1/2 x plus 1/2. And that's what we would write here, negative 1/2 x plus 1/2. All right, to find the x-intercepts and the y-intercepts, you know those steps. The algebra's not that hard. I think you can handle those on your own. Let's answer the question, does the function q of x cross the horizontal or oblique asymptote? So we don't have a horizontal asymptote, we just have an oblique asymptote. So we're going to take our function q of x and see if it ever crosses the oblique asymptote. So if they cross, then that must mean there is a point where they're equal to each other. Let's see if we can find it. So q of x is negative x squared plus x plus 2 over 2x. And that must equal negative 1/2 x plus 1/2 if they are to cross each other. So we're going to multiply the left and multiply the right by 2x. That's going to get rid of my denominator on the left. So we'll have negative x squared plus x plus 2 equals negative x squared plus, let's see, x. Well, let's keep our equation balanced, but we can add x squared to both sides, and we can subtract x from both sides. That will leave us with a positive 2 on the left and a 0 on the right. Is 2 equal to 0? I think not. So just like in our last problem, the answer here is going to be no, they do not cross each other. So I know that was a long video, but asymptotes obviously have a lot of steps. You have to check for 3 different types of asymptotes, and it can get pretty involved. So I hope this video was helpful and that you guys are all crushing your homework 10.